Okay, welcome back. I'm going to do some exceptions to the octet rules here. Not exceptions to, I'm sorry, I mean multiple bonding and expanded octets first. An example of multiple bonding. Let's say they wanted you to write the structure for oxygen. So we look up the valence electrons for oxygen, and we get two oxygen atoms, oxygens in group 16. So that gives me 12 valence electrons. Now what you're supposed to do, here there's no central atom. There's only two atoms, so both of them are terminal. And if you try this with a single bond and then complete the octets, the difficulty with this is it's the incorrect structure because you are using a total of 2 electrons for the bond plus 12. That means that we would need a budget of 14 electrons to create a single bonded oxygen molecule. That's not possible because oxygen doesn't have 14 electrons. It only has 12. In other words, we ran out of electrons trying to complete this the normal way. So what you have to do is you have to go back, get rid of these extra electrons, and try a double bond or a triple bond. Now my advice is try a double bond first. They're more stable and more common than triple bonds. So when we double bond the oxygen, those two overlaps require 4 electrons, and that leaves me 8 to complete the octets, and that works out perfectly because each oxygen requires 4 electrons to complete its octet. So if you look at the first oxygen right here, then we have 4 electrons from the unshared pair, plus the double bond involves 4 electrons, so you're looking at a total of 8 electrons. Okay, second example. Suppose you're dealing with a polyatomic ion, like cyanide. You're going to treat it the same way you would a regular molecule, except for you have to account for the charge. In other words, when I do my budget of electrons, carbon's in group 14, nitrogen's in group 15, and then you add 1 for the charge. So if it's a negative charge, then you're dealing with a surplus of electrons. -2, you'd add 2 electrons. If it's a positive charge, then you're dealing with a deficiency of electrons. You would subtract them rather than add them for the overall net charge. So this gives me 10 electrons in my budget. So again, there's no central atom. There's only 2 atoms. And again, if we were to do this, then we would have 2 electrons for the single bond, and then we would need 2 more here, 2 more here, 2 more here, 10, 12. We would need 14 electrons to complete this, but we only have a budget of 10. So that means we got to try some double and triple bonding. Now, if you're off by 2 pairs and you only have 1 connection between atoms, we can go back and we can do a triple bond here. That will use up 6 of the electrons and leave me 4 to complete the octets. But if each of the atoms already has 6 of the 8 electrons, then the carbon and the nitrogen need 2 more. Lastly, if it's a polyatomic ion, you put brackets around it, and you put the overall net charge outside the brackets. All right, so suppose we had NH4 plus. Again, we set up our budget. 5 valence electrons for the nitrogen, plus 4 times 1 electron for the hydrogens. And then we're going to subtract an electron because of this positive charge. So that's going to give me 8 electrons to deal with. We know the hydrogen cannot be a central atom, so we connect the 4 hydrogens as terminal atoms. And that uses up all of our 8 electrons, but we've satisfied all our octets. Nitrogen has 8, hydrogen only needs 2 from the bonds. We just have to remember to put our brackets around it and then put the positive charge outside to complete the diagram. All right, suppose we had something like this. Sulfur Hexafluoride. So we go and we try our technique with the valence electrons. We set up our budget. Sulfur's in group 6, so 6 electrons. And then there's 6 fluorines that are in group 7. So that's going to give me 48 electrons. Now, we know the fluorine cannot be a central atom. The sulfur's got to be a central atom. All right, so we put the sulfur in the middle. Now, the issue is, where do we put all 6 of these fluorines? The way this works is that we're going to put one fluorine north pole, one fluorine south pole, and then we're going to take the others and spread them out equally on the equator. So into the corners of a square, we'll put a fluorine. And we'll learn a better way of diagramming this a little bit later. So that's going to use up 12 of our electrons and leaves us 36 to complete the octets, which is good because each of the 6 fluorines requires 6 more electrons. Now this didn't follow our rules for writing the Lewis structures. We knew this had to be an expanded octet, and the reason why we knew it had to be an expanded octet was because we had 6 things connected to a central atom. So that's automatically going to violate the octet. Now sulfur can get away with it because sulfur is a period 3 element. It has d orbital spacing, and we can use that d orbital spacing to create the molecule. As it turns out, a lot of times sulfur is more stable when it has 6 things connected to it than when it has 4. Let's try this next one. We have xenon tetrafluoride. So wait a minute, xenon's a noble gas. It can't react with anything. Well, under normal circumstances, it won't. But man-made environment, under high pressure and temperature, we can get it to react and we create this particular stable compound. So we're going to set up our budget. Noble gas, 8 valence electrons, and then 4 times 7 for the fluorine halogen. That gives us 36 electrons. So again, we're going to put the xenon in the middle, and then we're going to connect the 4 fluorines. That's going to use up 8 of our electrons and leave us with 28. Now, that's going to create a problem because each fluorine only requires 6 valence electrons. That's only going to use up 24 of our budget. And so the rule is, rule 5, that when you have electrons left over, you use them to expand the octet. And what that means is we're going to put those extra electrons in pairs on the central atom. And we'll just spread them out. And there you go. There's our xenon tetrafluoride.